Hello, good afternoon. Today we will be discussing a very important topic in operation and supply chain analytics, and the topic is Six Sigma and statistical quality control. So, Six Sigma is a very important concept. It's a philosophy and it's a set of methods these companies are using to eliminate defects in their product and processes. So you will see many companies mentioning in their publicity material or on their website or in the marketing presentations that they stick to Six Sigma quality in their operations or in manufacturing processes or in service operations. So basically the Six Sigma, the purpose is to reduce variation in the processes that leads to product defects. And ultimately Six Sigma is a quality initiative. It's a quality method that company use, and they want to reduce a measure called DPMO. The full form of DPMO is defects per million opportunities. The formula for DPMO is number of defects divided by number of opportunities for error per unit and number of units. So this ratio gives you the defects per million opportunities for that particular product or a unit where the defects can happen, and how many defects per million such opportunities are there. And intention is to reduce the number of defects in a service process or manufacturing process or manufacture unit or service instance, to reduce the defects per million opportunities as less as possible. So you can only reduce something when you are able to measure it. So DPMO is a good measure. So let's in Six Sigma, the way to go with this method is DMAIC cycle, which is a very popular acronym, and it's D in DMAC stand for D is for define. In define, you identify customer and their priorities. In M, you measure. So once you know what customer, what specification they want, then you determine how to measure the process, how to measure that particular specification or that particular parameter or certain quality characteristic, and then how it is performing. So once you measure it, then you analyze it. You analyze what is causing that defect or what is causing that particular problem or issue. So once you measure it, you know it's above a limit or it's something problematic, then you analyze the likely causes. And once you know the causes, then you try to remove those cause of defects. You try to improve on it. And then next is control. So how to maintain the improvements and how to keep on continuously improving. And DMAIC cycle is ongoing effort, and once you do a DMA cycle, you improve the quality to the certain specification that you want, and in future again you want to repeat it so that some other parameter would have got maybe creating a defects now, or some other process step may be faulty, and then you when you make the DMAX cycle, you keep on improving on them and making sure that your processes, be it service processes or manufacturing operation processes, they keep they keep meeting the quality requirements and they keep meeting the customer requirements. So what are the some quality tools in Six Sigma? So first is a flow chart, which you use Six Sigma. Once you try to operationalize it, you some analytical tools are helpful, and first tool is a flow chart which gives you a sequence. I'll just show you in a while. First is a flow chart as diagram sequence of operations. Then there's a run charts. It shows trend in data over time. Pareto charts. So we take flow charts and the run charts. Then Pareto chart helps to break down a problem into components. Check sheet is a basic form to standardize data collection. Cause and effect diagram shows relationship, also called fishbone diagram, shows relationship between causes and the problems that are due to those causes. Opportunity flow diagram used to separate value added from non-value added in a flow chart. In process control chart, we will be discussing in detail today. We will be looking at how to assure that processes are in statistical control. So let's quickly look at the one by one. First is a flow chart, and it shows the major steps in a process. So it's a simple process shown here where you're trying to take photocopy of original document. So process steps are put origin in the glass, close lid, adjust setting, press start, and remove. So once your copy is done, you remove the originals, right? So these steps can be easily shown using the flow chart, and it says what are the supplies, what are the input, what is the process, and the output, and who are the customer. Next is opportunity flow diagram, the same flow chart where you put what is the value add versus non-value add in a particular flow chart. So you can see the same diagram where you're trying to take a photocopy of a document, and all the value added where some activity is happening and it's adding value to the whole process or the whole flow, that is shown on the left side on the value added, and there's a sort of a dotted line here. On this side you put all the non-value add activities. Sometimes you can also highlight the value added versus non-value added in terms of the colors, but most of the time we shows on them two separate sections. Next is check sheet when you want to collect the data, and then this is very important to do data collection efforts. So check sheet basically define what data is being collected. Suppose you somebody is on the factory floor and he want to do what is a machine downtime, and then he want to see what are the common causes. So particular person on a particular date will do the reason for machine downtime. So all the reasons are put in one column, and the frequency, number of times a problem dumb machine has gone down because of particular problem is on the second column, and some comments are also given. So here you can easily check what are the most common causes for machine downtime, and then you can take steps to improve on that. Run charts is also basically takes care of shows a data trend, and for example here average monthly volume of delivery per shop, and you can see the volume over the period of time from Jan to December in a year. The units have gone from 900 to increased all the way to 2400, then dropped. And of course this line is the average line, is a mean line, 1951 delivery. So you can see the trend of data over the period of time using the run charts. Cause and effect diagram, I told you, tells the what are the problems. Suppose a pizza is coming late, this is the problem. Or in other term I can say this is the effect. So late delivery of pizza, and these are causes can be in different components. So it could be pizza is late because of some machinery issues, and then some method issues. A problem because of issue could be, causes could be people related, or causes could be related to the material. And then we further break down these machine related causes to further one level down, and then we can, if we keep on drilling down, and then we can figure out that maybe it's a capacity issues for peak period, and then we can say maybe poor training, or it could be because of lack of experience of the cook to handle the large orders. So these could be the possible causes, one few among the many causes which are eventually leading to the effect or the problem. And then once we are able to uh, figure them out, we can take efforts to address those causes and improve on them. Next is process control charts. Basically, this is using statistical quality control. We will be looking at some process, some characteristic of a process. We are measuring it, and it shows the mean line, and this is upper control limit, and this is a lower control limit. And if the process characteristics, the process that we are measuring remains within the upper and lower control, that is okay. It should be around the mean. But if it's something is above the upper control line, or it's low below the lower control line, then it's something a problem, process is in problem, and try to we should try to address it. Center line usually is average, and we will discuss more about this process control charts as we discuss statistical quality control, and you will have more clarity on that. Few other Six Sigma tools that are used is failure mode and effect analysis, FMEA. So what you do is, like, what are the possible failures in at each stage of the process? You look at what could be the possible failure, and then you try to identify, estimate, prioritize the possible risk at the each stage of the process. And then once you know what are the different risks in each stage, then you try to, and you have prioritize them, and then you evaluate and try to address them. Design of experiment is a statistical methodology to determine cause and effect relationship between process variables and output. So suppose you have many process variables, and then you permit experiment, you go do experimentation with it and say what are the different combination of different variables, what are their values, uh, and because of these process variables, what is the effect on the final quality characteristic that you are have interest in, or that you want to keep control on. Lean Six Sigma is also very buzzword nowadays, and basically what Lean Six Sigma is, like, you have uh, quality control tool of Six Sigma, and then you put it inventory management concept of lean manufacturing. So it's like reducing the waste and keeping the as less inventory wastage as possible, while putting Six Sigma process control, so trying to achieve high quality with low wastage and low inventory. Lean manufacturing is sometimes it's very popular nowadays. It's basically minimal cost and using of concept like JIT, just in time inventory methods. And when you can always mix it with Six Sigma and come up with Lean Six Sigma in service operations or in manufacturing operations. So what are the roles and responsibility when an organization is trying to implement Six Sigma? So of course, the executive leadership must champion the process of improvements. So once you have top management is championing the cause, then you have corporate wide training in Six Sigma concept and tools. So once people are trained, uh, and how they know about Six Sigma tools and how to implement them, then management should give them stretch objectives for improvements, and they should be continuous reinforcement and reward. So it should not be a one time uh, motivation. It should be continuous reinforcements, and reward should be provided so that people remain motivated and keep on implementing Six Sigma continuously. So okay, let's Six Sigma. So you could have made sense that DMAIC cycle and using the different tools. Of course, some statistics is involved in uh, implementing Six Sigma in detail, while it comes to service operations or service processes or the manufacturing operation processes. So now let me take you through some concept of SQC or statistical quality control, so that some statistical term that we used while we talk about Six Sigma becomes clear to you. So SQC is a wider concept than Six Sigma, and it talks about number of different quantitative techniques. So that these quantitative techniques to basically evaluate quality from the conformance. So we want certain quality characteristic to be of certain we can of certain value or some prefixed quality parameter value, and then we can evaluate quality whether it's conforming to that particular measure or standard, and then once we evaluate it vis-a-vis a standard, and then we know how to improve on it. So because we know process inherently some variation in manufacturing, service operation in particular, a lot of variation because humans are involved. But in manufacturing process also, even machines are working, we have some variation in the output. We will discuss just in 2 minutes more about that. So variation in a particular manufacturing process, or even it's more in service processes, are caused by factors that can be clearly identified, and then we can even manage those factors to reduce the variation in the process, or in other terms, to improve the quality and keep the quality constant or keep the quality high. So assignable variations are we can identify the factors and who are causing the variation, and then manage those factors. But some variations, common variations are there that are inherent so sometimes they are also known as random variations, so we don't know what are the causes, and they even how much factors we manage it, they still remain in the process. So one common way to measure variation is mean. So you have average value. Basically mean is average value of set of numbers, and suppose you have observed value, so you have a sample of n, and n can be any number, let's say 10, and so in 10 observations of say a diameter of a tool, and so in sample size is 10, and you observe the diameter which is supposed to be 1 inch, and you observed it's 1.1, 1.2, and you average those observations over the total number of observed values, and you get a mean. And in a set of number, standard deviation is a measure of variation. So and variation will be around the mean, of course. So once you know, so standard deviation is measured by is a measure of variation in a set of numbers. It's denoted by a sign called sigma, and there are many different ways to calculate it, basically depending on what distribution it is following. Is a normal distribution, Poisson distribution, or uniform distribution. But one common way to do standard distribution is the observed value, the difference from the mean of the sample, the square of it, summation I to n, and square root, and this divided by n, the total number of observed values. So normally when we want to reduce the variation, so when variations goes down in a process, the quality goes up because you have more confidence in saying that the output of the or the product characteristic meet the certain value that is prefixed or predetermined. So of course it is impossible to have zero variation. So I just told you, suppose in a you are making a latch, and latch has a diameter of 10 inches, and of course it will not never be 10 inches all the time. Sometime it will be 10 inches, sometime it will be have variation of plus minus 0.2 inches. Sometime it will be 0.01, sometime 0.0005. So it will lie between the range of 10.02 and 9.98. So let's two things which are very important is to talk about specifications. So when we talk about upper specification, it's a maximal acceptable value for a characteristics, and lower specification is the minimal acceptable value for a characteristics. And so you have to understand there is a difference between process limits and process control limits and the specification limits. So suppose we want to measure a process capability. So capable, the mean and standard deviation of processes are operating such that upper and control limit are acceptable relative to upper and lower specification limit. So if the upper and lower control limit or the variation within the process with a certain high degree of certainty, so process variation is less than what variation is allowed by the customer, then we say the process is capable. So or another side, process control limits are less than the customer specification limit. So let's understand this thing from a diagram. Suppose you are doing a process where the mean is 1.25. This is the mean. And here you have, this is lower control limit and this is upper control limit. Where, but your upper spec limit is, oh, okay, I have to little bit of correction there. Okay, this is what customer want. So this is yeah, okay, I was correct. This is upper control limit, this is lower control limit. But you can see your process specifications is here. So this is of course, this is more than, and this is of course in negative sense it is more than this. So you have variation here and variation here. So this is, you can say process is not capable because your process is varying more than what customer would have allowed through using control limits. So let's see one example. Okay, now here it is lower control limit, this is upper control limit, this is something that is allowed by the customer, and here is your process. Now the mean remain the same, but the process upper specification limit and the lower specification, now you can say they are less, and here this is also in terms of negative it is, yeah. So you have, this is good and this is good, now you can say your process is capable. So your process specification, the variation in the process is less than what customer specification or the design specifications are there for that particular process. How do you measure it? One way to do that is it's a ratio. We have a process capability index. It's a ratio of range of values produced or values divided by the range of values allowed. So basically process capability index CPK is equal to minimum mean of means minus lower specification limit and then 3 sigma, which is 3 times standard deviation, or the minimum of either of them, or upper specification limit minus mean of means divided by 3 sigma. So it shows how well the parts being produced fit into the range specified by the design specification. So normally we would like to have CPK larger than 1. So if CPK minimum of these is more than 1, that means process is capable. Yeah, when two numbers are not close, that means has shifted. So let's look at one example where there's a manufacturing process where you're putting pressurized oil in aerosol. So these are like putting a deodorant in a aerosol can. So the pressure, the design specification says that upper control limit is, this is 60, pressure is 60 psi plus 5. So 65, and the lower control is 60 minus 5, 55. So 55 is lower control limit, 65 is upper control, and average is 60. Sample average, then you figure out the sample average, which is mean of means is 61 psi pressure, and standard deviation is 2 psi. So let's figure out whether this process is capable or not. So first is we interpret the data. Lower specification is limit is 55, upper is specification limit is 65, mean of mean is 65, standard deviation 2. We calculate process capability index, which is minimum of 1 or 0.667. It comes out to minimum is 0.667. So this means it's a not very good capability index. This process capability is not good, and it can definitely be improved. And then we can also use the information here to calculate probability of a defect using statistics. And Z we all know is like difference between observed minus mean of means divided by standard deviation. So Z at the 55 is minus 3, and Z for 65, upper control limit is 65 minus 61, that is mean divided by sample mean divided by 2, which is standard deviation. It comes out to be 2, and we find out the value at value of P at both the thing. So P value is minus 3 is 0.01398, and at normal distribution for 2 is 0.002. So P of less than 55 but more than the area comes out to be 0.024. That means, and this equals 2.4. That means 2.4% of the products will be defective in this process. 2.4%. So from the probability, this is the interpretation we have. And let's look at process control procedures. So sometimes when we have a process ongoing and then you want to monitor quality while the production of a service or a particular product is going on. So in SPC, you take a sample. How do we go with that when something is is under the process of manufacturing or service operation processes? Then you take a sample, and then when you take a sample, you say this process is producing items, or this service process or production process producing item or service which is within a pre-selected range. And then we take a sample, then what do we measure actually? So when we take a sample, it has certain attributes. Like attributes are called quality characteristics that are classified as either conforming or not conforming. Suppose we take one attribute, say we take suppose we are making aerosol can, just for example, and we take the pressure in that can, right? And then this is a variable, this is a characteristics which we're going to measure using we're going to actually measure the pressure, and this is a variable of interest to us, and this is a quality characteristics, and whether we say whether it conforms to 65 psi or not, or sorry, 61 psi or not, something that could be an attribute, quality attribute that need to be adhered to. So we're going to measure the variable and then see whether it meets the particular attribute value that is assigned to quality for the quality measurement or not. And process control chart we just explained you earlier in this presentation, but we'll come back to it. So once you have this lower control limit and upper control limit, and then you measure this characteristic, and the center line is of course the mean, and then you keep on measuring this characteristic quality parameter, that or the particular variable you take a measure it, you take the values here, and it's around the center line, which is normally the mean. So if it is around this, then it is a normal behavior. But if something goes, one point goes above the upper control limit, then this is a cause of concern. And if or there is a point below the lower control limit, then it's also, then we say process is going out of control and we need to put back it in control. Then if there's a 2 points near the upper control limit, also investigate for the cause of poor performance. Similar for 2 points near the lower control limits. 5 points above in the same, in the from the mean line, or for the 5 points in the same side and continuously rising, that also calls for concern. Similarly for downside also. Trend in either direction is a cause that it may eventually go out of control, so that needs also need to be checked. Same is sudden change in level or erratic behavior need to be changed. So if we are measuring the quality parameter or the quality variable and plotting it on a control chart, we can keep the process in control by the graphical inspection and then take remedial steps. And three things which are very important when we do these charts. The three type of charts, control charts, are very popular. One is called P charts, and then X charts and R charts. So let's look at first P chart. So P is basically used when item or service either good or bad, yes or no decision, and we normally say P bar is normally total number of defective units from all sample divided by number of samples and sample size. This is a formula. Standard deviation of the sample is basically this probability into 1 minus P divided by the sample size. Upper control limit is probability of the defective units among all the samples plus Z, and then this is standard deviation with the probability curve, and our lower control limit is the mean value minus, or this probability of defective unit among all the sample units minus Z, and then this is the standard deviation, sorry, SP is the standard deviation. In case this, either it's going to be 0 or it's going to be this value P minus ZSP, that is lowest control limit, and upper is P bar plus ZSP, and Z normally we take, because of 3 sigma, we take Z is equal to 3. Let me give you how to create P charts. First we calculate the sample proportion for each sample. We're going to have one solved example that will clarify. Then we calculate the average of the sample proportion, calculate the standard deviation of the sample proportion, calculate the control limit, plot the individual sample proportions. And then, for example, let's look at this number. We have 10 samples. In each sample, we have 300 units. And these are defective units, the defects. So you can see this number fraction defective is 10 divided by 300. This is 8 divided by 300. This is 9 divided by 300. And total 10 samples, 300 each. So total sample is all samples. The total size is 3000. Number among all the 10 samples, total number of defective forms are 91. So this p hat will become 91. 10 samples, sample size 300 is become 0.03, and SP is 0.0099. So upper control limit becomes, yeah, P, which is 0.03 plus 3 times 0.0099. So it become 0.0099. Oh, yeah. And upper control, no, this is upper control limit becomes 0.06, and lower control limit is 0.03 minus 3 times this, so it becomes very less, around 0.00063. And then, so this is upper control limit, this is lower control limit. Then you plot all these fraction defective here, then you plot them here, all the values here, and definitely the all of them are between, so our process is in control, we can easily say that. X chart and R chart, we draw them using same thing, but in upper control chart, the mean of means plus A to R, lower control limit is mean of mean minus A to R. Normally when we take a small sample size is small, around 4-5 units, but number of samples can be 25-30, large number of samples. Frequency between cost of sampling and benefits of advice. So you have a trade-off between cost of sampling and how big you want the sample size, sampling efforts to be. Control limit, this value is A2. Normally we will take this value to be around 3. This A2 is basically Z, and like I showed you in earlier in P charts, here also we take those things as this value as to be 3. So let me give you an example. Let's go to a can filling machine thing and give you an example using Microsoft Excel. And if we come here, you can see here we have taken these 20 samples are there, and each we take the average, correct? And here is, this is mean of means, means whatever the sample means, there we have taken the mean again. So we can say equal to average and we can select, and then this is the standard deviation of them. Okay. Yeah. The number Z we have taken 3, so upper control limit becomes mean of mean 1.7 plus 3 times standard deviation. So this become value become this, and this is lower control limit. So same values go here, all the values are upper control limit here and the lower control limit here. And then probability of defects, basically we are just, the same value. Yeah, this one goes here, correct. Now we gonna plot them, this value between this and this, and this value become our mean value. So you can see here, this is 1.72, upper control limit is 2.08, lower control limit is 1.3, and all these values are plotted here. So we can say that yes, our calculation in terms of uh, the can filling and the process, the characteristic that we are measuring remains between both the upper control and lower control, and the process is in control. Now let's come back to R charts. Yeah, then how to calculate R charts, and let me again take you through Excel to show it to you. So in R chart model, of course, you have sample, and then you have range given and mean of ranges. Then you find mean of ranges, which is average of all these ranges. And for total sample size of 10, you know this is 0.03 and T34. This is from the table, that is standard table provided to us. So upper control limit becomes, yeah, mean into the table value, and this multiplied by this. Yeah, so you can see, sorry, it's other way around. This upper control limit and lower control limit, this both the values goes here, and the mean of mean goes here. So you can do a chart here, and you can see again here, this is upper control limit we have plotted, this is lower control limit we have plotted, 0.04, 0.32 upper control limit, and then mean 0.18 is plotted here, and all the sample ranges are plotted here. So except barring one point which is above the control limit, which calls for, so it's like 0.10, there's a cause of concern that need to be investigated, otherwise the process looks, but here is there's a cause of concern because 1 point is above the upper control limit. So with this process need to be investigated, what is the reason, and then process may be recalibrated. So now let's now look at so we just now we discuss suppose an ongoing process, but sometime in a warehouse you get goods which are delivered to you. So far we have, what we have done is at the organization level how to set up the quality process using Six Sigma. Then we understood what is statistical quality, some tools that are available to us. Then we say, okay, suppose some process is running, then how to implement using sampling, how to implement the quality process measurement and statistical quality control into it. The next is suppose you have a finished good, you're dealing with finished good and something in inventory, or so you export some item is imported, and you the goods have come to your warehouse, and then in the inventory you want to see what is the quality. So one way to do this, like on good that already exist, so we try to figure out what percentage of product conform to specification. and then we trying to do it using why we do that is we to determine the quality, and then make sure that whatever once we know what is the quality level in that particular inventory, then we make sure that quality is within the predetermined level. And how we do it, we from the large inventory goods, we go through a sampling plan, we take a sample, and based on that sample, the whatever the percentage of defective item we allow it through based on our sampling plan, then we accept or reject the lot. Suppose there is a total good 1000 have come, we cannot check all the 1000 items, so we take, say, let's say sampling of 20 items, and then say okay, if five more than 5 items in those 20 items are defective, then I'm gonna reject the whole lot. So this is what just one example of how we do the acceptance sampling when the goods are there already in inventory. So there, of course, there disadvantage, risk of accepting bad lots and rejecting good lots. There is of course planning and documentation. And when you do the sampling, this is of course the information that you have is because you have not invested the whole 100 items, so you have less information because you're only inspecting 20 items. Advantages are it's economical, there's less handling charges, fewer inspector required, and there's of course uh, you know there's a motivation of improvement how you go through the sampling process. So how to go about doing this as designing a sampling plan, like suppose you say n units from a lot, you sample n units, sample size is n, and then maximum number of defective items c. So you decide on how many maximum number of defective items c that are allowed. AQL is defined as maximum acceptable percentage of defective designed by producer. So if your producer say, okay, sir, kindly, accept the lot if more than 95% of the product or are okay. And then there's another thing called from consumer. This is a producer. This is also called the producer risk. And the lot tolerance perspective is percentage of defective that define a customer's rejection point. So this is all consumer risk, lot tolerance percent defective. So producer risk, alpha is a probability of rejecting a good lot, and beta is a consumer risk, probability of accepting a bad lot. So producer risk alpha is because suppose you send a good lot and only luckily, and you say okay, 5 units are, because 95% from your side are okay, and they take a sample and all the 5 units are there in that are defective, so your lot will be rejected, but 95 are good. So that's a risk you have. Consumer risk is suppose in 100 items and 10 items were defective, so 90 was there, but you took a sample and in sample only 2 units were defective, so you accepted, but in fact 10 units were defective. So that is the risk on the consumer of accepting a bad lot, while on the producer the risk is rejecting a good lot when he sent a good and customer rejected. That's a producer risk. We will look at it when we draw the graph. The way we measure this thing in statistical quality control is through operating characteristic curve called OC curve, and it shows the discriminative power of acceptance sampling planning. So what OC curve does is basically on one side your probability of acceptance is there on y-axis, and then so probability of accepting a lot, and here is fraction defective. Yeah, and when you do it, the sampling risk are known to you. So I just gave you example. We stick with it. C n is equal to 99 and C is equal to 4. So this you can see here. This is approximately 5%. This is a producer risk. At 5%, normally you can say 2 products. And this is called AQL. Acceptable quality level. And then you keep on increasing it. So beta, which is consumer risk, so 10%. Probability acceptance go below the 10%. So this become beta, which is 10%. And of course here is a 5%. This is beta is 10%. And this point, percentage defective, it's called LTPD, lot tolerance percent defective. Okay, so this is let's go through an Excel and then try to see. AQL is also defined as percent defective that the plan will accept 95% of the time, and LTPD is also defined as percentage defective that the plan will reject 90% of the time. So let's go through one example in Excel and see how we can do this thing in Excel. So let's go through. So sample, there are two samples here. First sample is 170, n and c is you allow is 5, and then you change n to sample size to 220 and number of defect unit allowed in sample to be 8. Yeah. So at this level, AQL for the first 2% and LTPD is alpha is 5 and beta is 10. And how do we do that? In the first case, we have cumulative probability percentage defective. This is for the first and this is for the second. And you come up with, and of course this OC curve follows the Poisson distribution. So you have probability of acceptance here, probability of defective, percentage defective here. And so you E4 in this case is C, which is number of 5 units, defective units you allow. Then you choose E11, which is percentage defective from here. Yeah, and then you put true. So this gives you the cumulative probability of accepting. And what you do here is here you find out the mean, which is E3 sample size multiplied by cumulative probability. Sorry, the probability of effective. So it's E3 versus B11, and you keep on calculating here. And this is basically what you're trying to do is you're trying to put this graph here. And then you figure out the alpha. Alpha is if, say, if this value, percentage defective, equal to AQL, acceptance quality level, which is 2%, then it takes the value of 1 minus C13, 1 minus C13, 1 minus 0.87. So which is 13%. So you can find out here. So alpha becomes here, and then beta is other way around. If B17, this value equal to G4, which is LTPD, then you take the value C17, this value. Earlier we were in alpha, we were taking 1 minus this. So for LTPD, we have to, then it becomes 2%, 6%. So you can see here it is 6%, and this is LTPD, and 2% is AQL. Both of them are plotted here, and this is how you, so as the percentage defective goes high, the percent probability of acceptance goes low. The same thing, one more chart is there where we are trying to figure out AQL and LTPD. Sample size is 200. The number of defective allowed is 5. So we have to find out AQL and alpha. Alpha and beta is given. AQL and LTPD. And what how we do is we have mean and percentage defective. These are given to us. Cumulative, as I told you before, we try to figure out the Poisson distribution value, cumulative probability, and cumulative probability comes out to be, yeah, for this the mean and true. So cumulative probability keep on, as the mean keep on increasing, the probability goes down, and alpha is of course 1 minus this, and beta is of course this value. So let's say alpha 2. So we're looking at alpha at 10%. So you can see here at one point approximately 1.4, the value here will be around 10%. So AQL becomes 1.5, and as this thing keep on going on, so approximately around 4% between here and here, we this thing will become around 10%. Consumerist will become 10%. So it answer is around 1.5, and this is around 4.5. So using Microsoft Excel, we can easily figure out the acceptance quality level and the lot tolerance percent defective. Thank you very much. I hope you will be little bit knowledgeable about Six Sigma now, and the statistical quality control, and what are the common tools, and how and why we implement it in the manufacturing and service operations. I look forward to talking to you in more videos. Thank you very much.